Okay, now, on the previous tutorial, when we talked about the Monte Carlo, we learned that there is a very interesting applications of using the very high number of trials that we can always comes for this very interesting estimation that f of x into p of x as a distribution of the x dx can be equal to 1 over n, which is going to be the average of all the evaluations of the x coming from this distribution, I from 1 to n, all coming from 1 to n. However, we learned that n has to just go to the infinity in order to have, I should say, high number of the trials to get approximate this integral into this sum of f evaluated at each x taken from this distribution. It was the thing that we just covered that on the previous tutorial. However, the thing that I'm just going to talk about here is going to be this distribution, the p of x, which is not always going to be something that we expect to have easily samples drawn from it. And what do I mean? In cases that, for example, we're just going to have some examples in the next tutorials that we'll see that we can just have some distributions that taking the samples from them within this integral is not going to be easy. Then the thing that we do, we just have a kind of an, if we can just call that an auxiliary. That's what we call that. We call that, for example, an auxiliary method. For a proposal, I should say, distribution. And what do I mean? I mean this. For example, imagine that if I just go back to the same integral that I was trying to solve, imagine that we have essentially our original f of x, and we have our own p of x. However, the thing that we do, we just come here, we use an auxiliary distribution, which I'm just going to call that q of x, more divided by p of x. P of x is divided by q of x, and I have q of x here, and also I have the rest of my integral like that. You see that the thing which I have done on this example, it's not something very bizarre. Why? Because you see that the things which I have created here, I have at the denominator an auxiliary, I should say, distribution, which we call that the proposal distribution, which is exactly has been multiplied at the numerator, but the same thing. You see that these two things essentially shows that, for example, if you remember from the things that we have done that in the elementary math, we saw that, for example, a is essentially equal to a if you divide a by b, but at the same time multiply that to b, because you see that from both the numerators and the denominators you can just remove the b. And that's essentially what has been done here. We just call this, I should say, q of x as a kind of a proposal distribution. And we see that the thing that we can do is this. We see that in our model, still we can just use the same Monte Carlo estimation. However, in this very example, we see that the thing that we can just do, we just come here to just write this, the sum. We have the sum. However, the sum that we are just going to write is going to be something very easy. Look at this part. Initially, we evaluated, I should say, the functions f of x, and now it seems that we are not taking samples. We are not making the draws from the p of x as what we did originally do. And now it seems that instead of drawing samples from the p, we are drawing samples from the q. And then as a result, the thing that we do, we just come to evaluate this function now, f of xi times p of xi divided by q of xi, which is going to be I from anything from 1 to n, divided by 1n. And that's essentially, that's what we did. Because now here, if you can take a look at the distribution which we have right now, you see that the distribution now, it's somehow, this is this function that is being evaluated at each point xi, which is drawn from this distribution, which is going to be the q of x. And now that's what we see here. That's this function now, that this is being evaluated at each point drawn from now the q of x, not anymore from p of x. Okay. And now, there is, before we just move on to do some kind of, I should say, simulation, I should say, on the R, we will see that if we have, let's say, for example, this term which we have here, which is going to be p of x divided by q of x, we can call it w of xi, which we call that essentially, it has a term for it, we call that importance weight, which these ones can be used as a very important diagnostic phase, I should say, for the models that when we just come up, let's say, with a proposal, I should say, distribution, because as you are going to see in the next, I should say, tutorial, the thing that we're just going to do, you will see a very important characteristics of the q of x, that q of x should not have an infinite variance. Then if it happens, then I should say the results from, or you should say your numerical methods, the thing that you have done is going to be unreliable. Then as a result, in just 1 minute, I'm just going to come here and just summarize the things that we have learned before we just move on to the R, to just do some kind of samplings and to do some kind of, I should say, demonstration of how to just do the importance sampling. I'm just going to have a very quick review of the things that we did. Initially, we started with this integral. We see the integral of the f of x, p of x. That's the distribution that we normally see this formulation in, I should say, in the Bayes estimator of d of x can equal to the sum of all the f of x evaluated at each x drawn from, I should say, the p of x, from, let's say, 1 to n. However, we divided by n. But the important thing that we mentioned was that the n in this formulation should go to infinity. The higher and higher number of, I should say, trials and samples, we just repeat that experiment, then it means that we are just going to have a higher convergence. And as you remember from the previous tutorial, this convergence happens at the rate of, which is proportional to 1 over the square root of the n, which is the n is the number of the, I should say, the samples and the iterations that you had. Okay. But however, the thing that we learned right now here is that sometimes we can have the p of x substituted by an auxiliary distribution, which we call that the proposal distribution, and we can just write, I should say, this estimation by this method. And we say that, okay, this integral is going to be written by the f of x, p of x, q of x, q of x, d of x, which we see that, again, similarly as what we saw above, it should be equal to 1 over n of the average, that it's going to be, I should say, f of x, p of x, q of x. Each has been evaluated at the draws that now you had from the q rather than having it from the p, and now we have I equal to 1 goes to the n. And we know that also the same thing assumption is valid here, that the n should go to infinity. And also we can just write it in this formulation, that this one is equal to 1 over n of the sigma of f of xi times wxi, and I is from 1 to n, and we know that still the same thing, that the n is gonna go all the way to the infinity. Then as a result, we can say that, okay, we have converged this integral with this proposal, distribution, that this distribution doesn't go, it has not an infinite variance then I should say on the next tutorial, and also before we just leave, I have to highlight this fact that we call this one as an importance weight. We can just use these weights as a kind of a diagnostics on the analysis that we are just going to do when we just go on to just do, the leave one out cross validation on our Bayesian prediction and the model which we have produced then. And now we are at the end of this tutorial. On the next tutorial, we are just going to continue these sessions and have more interesting stuff. See you later.